Okay, so the last time we were here, we were talking about standard deviation, and I told you that I would walk back through this calculation, and then I'm going to show you the hard way, and then I'm going to show you the easy way. Now, just because I'm showing you the hard way first doesn't mean that you should ignore it, because it turns out that learning this now will help you in Chapter 11. So you got to know how to do it this way for Chapter 11. So here we go. The first step we said was to turn all those percentages into decimals. And what we did was take 13.7 and end up with 0.137. How do you get from percentage to decimal? Divide by 100%, right? You divide by 100%, that gives you the decimal. So here we go. Let's get our calculators out and say 0.137. First thing we're going to do is figure out the average. So I'm going to add 0.137 plus 0.358 plus 0.4514 minus 0.888. What? Or 0.0888, sorry. Why did I do minus there? Yeah, it's a negative, right? And so this is my sum. How do I go from the sum to the average? Divide by the number, which is 4, right? So 4 equals. Now, here's what I want you to do. I want you to hit store 0. And you'll see why in a minute. We're going to be using that number again and again and again. Now, have I done anything magic so far? No, this is just plain, I mean, your grandma could do this, right? Okay, so now let's move on to calculating the sample standard deviation. Just a little bit of review here. That first column is the same set of returns that we just talked about. And the second column is something called the deviation. Now, how do you find the deviation? We're going to take the return for a given year, and we're going to subtract out that average that we just calculated. That's why I told you to put it in your calculator under 0, because we're going to keep using it over and over and over again. So for instance, what I'm going to do for the first one is I'm going to type in 0.137 minus, recall 0, and that's going to give me minus 0.0774. And I'm going to do that for all of those, and that'll give me a deviation for each one of them. And then the next step in finding a variance, this is actually, we're heading to variance first, is to square the deviation. What does the squaring of the deviation do to the sign? If it's a negative, what happens? Yeah, so a negative times a negative is a positive, positive times a positive is a positive. So all your squared deviations end up being positive. And we said the reason we needed to do that, if we just add those deviations together, they would be 0. The other thing we could do would be to take the absolute values and then find the average of those, and that's called mean absolute deviation. We're not going to use that. We're using standard deviation because we're headed for the normal distribution. Okay, now let's walk through each. Oh, by the way, most students, here's what they do. They figure out the deviation for year 1, and then they write it down. And they figure out the deviation for year 2, and they write it down. And they figure out the deviation for year 3. What do you think they do? They write it down. They figure out the deviation for year 4, and they write it down. Now, what do? For the next step, they go back and they re-enter those into their calculators, perhaps correctly, perhaps incorrectly, and then they square them. And what do then? They write that stuff down again. But do you think they necessarily write down all those decimal points? No. That one's like 0.006. Everybody knows that, right? Now, here's what I'm going to tell you. In finance, you can truly mess yourself up if you do that. I'm going to teach you a pure method that is both pure and simple and will return the actual correct number to you. It takes less time and it's less error prone. I hate being wrong, right? So why would I entrust myself to write numbers down and then re-enter them? Because I know these fingers don't work right. Okay, so here we go. Get your calculator up. First thing we're going to do, 0.137 minus, where do I have the mean stored? 0. I'm going to say recall 0 equals. And there we go. That's our deviation. Now, here's the revolutionary part. This is what most students don't get. The next step that we do is actually to square this thing. Let's go ahead and square it. And I don't have to retype anything, and there's the number, and all the decimals are there. Now, I don't want to write this number down, so here's what I'm going to do. I'm going to say store 1. Store 1. And it's in there. I can prove to you. Recall 1. Boom. There it is. Okay, now, what do you think we do next? What next number do I type in? Yeah, 0.358 minus, what am I going to do next? Yeah, recall 0, because that's what that means, hanging out, equals. So that gives me that deviation. What should I do next? Square it. Boom. And then what should I do? Store, where? 2, very good. Okay, now we've got 0.4514 minus what? Recall 0 equals 0.237, and we square it. What should I do with that number? Store, where? 3, very good. And then finally, I got to be careful here, 0.0888. What do I need to do next? I got to hit that minus, right? The plus minus key to turn that negative. And I'm going to subtract recall 0 minus 0.3032. What's my next step? Square it. What happened to the negative? Okay, it goes away, right? Minus times a minus is a positive. So what should I do with this number? Store 4. Okay, so the next thing we're looking for is called the sum of the squared deviations. These are the squared deviations. What should I do with these things? Yeah, just add them together. And how am I going to do that? Yeah, recall 1 plus, recall 2 plus, recall 3 plus, recall 4 equals. And that gives me the sum of the squared deviations. And from there, we go to variance. And by the way, we are calculating sample variance. We must divide by n minus 1 because we've already used some information from that data set to figure out the average. And so we're dividing by n minus 1. N is 4 here, so what do I need to divide by? 3. Divide by 3 equals. Now I'm getting 0.0582369. Is that the standard deviation? No, what is this? This is a variance. How do I get from variance to standard deviation? Yeah, just take the square root. Boom, there we go, 0.2413. Okay, now I am going to store this in location 5, and I'll show you why here in just a little bit. That's the math. That's the way. That's the method. And by the way, I'll be showing this to you again, right? You'll get to see it again. And if not, before you do your homework, you can always go back and watch this video and see how to do that. The key to the whole thing is using the memory in your calculator and working across, not down, right? The only time you work down is once you get over there to the deviation squared to add them together. It's a whole lot easier. Okay, so let's also figure out a simpler way to do this. So I want you to hit second and the number 7 on your calculator. What does the number 7 say above it? Data or data, depending on who you are, right? Data or data, and this is going to be a place where we enter data. Now, because the calculator remembers everything you've ever done, what you're going to want to do is, anytime you use this, is you want to say second clear work. And the reason is this. You can overwrite the previous data, but what if this time we're looking at 4, but last time we looked at 5? Well, you're going to have your first 4 data points right, and then you're going to have an extra one just hanging out there waiting to mess you up. So don't do that. You always want to clear it out. The other thing you need to know is that the calculator is actually designed to handle 2 sets of data at the same time. And so we're going to have X's and Y's. For the purposes of our exercises, we are only going to be using the X's. So we're going to put our number in here, 0.137, that's the first return. And then I'm going to hit, by the way, look up here top. There's your choices. Arrow up, arrow down, and INS. I guess you could buy insurance on it. I don't know. I don't use that. But here's what I do. I say hit enter, and as soon as I hit enter, notice the equal sign shows up. That tells me that the calculator now has my number. Now I'm going to arrow down. Y01. Remember I said we're going to leave Y alone. We're not messing with it at all. So just hit the arrow down key. What do you think I should put in for X02? 0.358, very good. And I've got to hit enter or it's like it never even happened. Then I'm going to arrow down. What do I do for Y?
Nothing.
Nothing, right? Just leave it alone. Arrow down. What do I put in for X03?
0.4.
Yeah, 0.45114. Enter. And then arrow down. Arrow down. And what do I do for this one?
0.0.
What else do I need to do?
Negative.
Negative. Most common mistake on this problem. People forget to put the negative. That's the most common mistake. Enter. Now, I've got all that information in there, but you know me, I'm paranoid, and I'm used to being messed up by the machine, so here's what I'm going to do. I'm going to arrow up and check and make sure that all my numbers are there. And they are, so I'm good to go. Now, the very next thing that I want you to do is look above the number 8. What's it say? Stat. You see these medical shows where the guy comes in with a knife sticking at him and they're like, get him to the operating room. Stat. Not the same thing. This is short for statistics. I don't even know what it means when they say that. Anybody know? I don't know. They just made that crap up. Okay, so stat here means statistics. So here's what we're going to do. How do I access the word above the number?
Second.
Yeah, so I'm going to hit second. I'm going to hit the number 8. And it says, by the way, this is a Chinese name, Lean, right? Do you think this is actually looking for a Chinese person? No, this is short for linear. Short for linear. This is what I've been told at least. Who knows? We're not going to do anything with that. But I do want you to look above it. Do you see it says set, arrow down, arrow up? We're going to arrow down. And the first thing that it says is n is equal to 4. What do you think this represents?
The number.
Yeah, it's the sample size, right? The number of items we're looking at, and it's 4. Okay, now, this is a good time to check. If you were putting in a sample of 4, and then this thing says 5, or 6 or 7, what did you forget to do?
Clear it.
Yeah, you forgot to clear it out, so that's your first check. Now, we're going to arrow down. X bar is equal to 0.2144. Do you recognize that number? Yeah, that's just the average, right? By the way, in statistics, when we put a bar over something, that's the mean or average, right? So that's why on this slide it says R-bar, because I'm not smart enough to figure out how to put the little line over the letter, so I just wrote it out, R-bar. Okay, now, arrow down again. And we have something that says S sub x. And here's something I want to point out to you. S sub x is the sample standard deviation. This is the population standard deviation. We are looking for S sub x. And by the way, do you recognize that number? Yeah, it's exactly what we came up with when we did it the hard, long way. And I'm going to prove that to you by saying minus, recall, 5 equals. Boom. No difference whatsoever. By the way, how can I get that number back? Arrow up, arrow down. Now, the next question is, if on an exam, instead of asking S sub x, I asked for the variance, what would you do? This is the standard deviation. What do I do? Mr. Nylon. You don't know, Ms. Wen?
Square.
Yeah, we're going to square it. So standard deviation, remember, is the square root of variance. So if it's the square root and I want variance, all I have to do is square it. And so that's what I'm going to do next. I'm going to hit this button. But I want you to notice what happens to the equal sign when I do. The equal sign goes away. This is the calculator's way of telling me, hey pal, this isn't really sample standard deviation. You have jacked with this number. And so, but I did manage to get my variance. Now, I want you to notice that the number up here that we have for variance isn't identical. And the reason is because the number that we have up there for variance is actually rounded to one less decimal place than what's on the screen right now. So don't let that freak you out. Now, the calculator will not calculate variance for you. This is the way to do it. This is the way. Now, I want to point something else out to you, and I'm going to show you this. By the way, when I was a little kid, and I'm hanging around with my mom, and my mom's cooking something nasty on the stove. She's not a great cook. She's cooking something on the stove, and I'm like, woo! I see the burner is like red hot, and it's so pretty. And I'm like, and she says, don't touch it. And I say, why? And she says, because it's hot. And I say, okay. Now, she has to turn around and get some horrid spice to throw into this. And what do you think I did? I'm getting ready to show you a hot burner. And I hope you're smarter than I am, because I hope you don't feel the need to touch this one on your own. And here it is. If I arrow down, what have I got? Population standard deviation. Is that what we're looking for? No. Folks, this is a hot burner. Don't go there. I used to not even show this to people, but you know what? Kids find things on their own. I would have found that burner whether my mom pointed it out to me or not, right? So I'm telling you, don't do this to yourself. Okay, now, what happens when I go back one arrow up? Bam, we're back to our standard deviation. If you figure out variance and you want to get back to standard deviation and you don't want to hit the square root button because you're really lazy, you could go arrow up and arrow down, or arrow down and arrow up, and it recalculates. So don't worry about that. Okay, now, any questions? Which do you think is easier? This way or the other way? This way. Do you have to actually know any math other than square and square root to make this work? No. Whew, okay. Now, we said that one of the reasons that we were headed towards standard deviation was because it goes into the normal distribution. And we said the other reason was because it's in understandable units. Standard deviation is in the same units as return as opposed to variance, which would be something like percent squared. Doesn't make a bit of sense to us as humans. So this normal distribution, we need to tell you two things about it. Number one is that the normal distribution is always centered on the expected value. The expected value. And there are different ways to get to the expected value, but for this example, it would be just the arithmetic mean, or what your grandma would call average, right? So that's the middle tent pole of this whole thing, is at the mean. And then the other thing you need to know is that the shape of this thing is dependent on the standard deviation. It's dependent on the standard deviation. The bigger that standard deviation is, the flatter this thing's going to be. The smaller the standard deviation is, the skinnier this thing's going to be. But these are the only two things that I need to define this distribution. Now you say, well, what good could it possibly do us knowing how to come up with this distribution? It allows you to come up with probabilities. Probabilities. So the first thing I want to tell you about the normal distribution is that if you take the mean and you look from -1 standard deviation below the mean up to +1 standard deviation above the mean, there is a 68.26% chance that an observation randomly drawn will fall in that spot. 68.26%. So that's pretty cool. Just within, we've got more than 2/3 right here, ±1 standard deviation from the mean. And then I'll also tell you that we have 95.44% of observations ±2 standard deviations from the mean. More than 95% are just ±2. That's pretty cool. And then we have plus or minus 3 standard deviations, which is 99.74%. Are going to be between those two. Now, for purposes of calculations, we often use estimates or approximations. And so this would be something very good to have on your note sheet. Did you guys hear that? This would be something very good to have on your note sheet. So we estimate, we round down to the nearest percentage, and we talk about plus or minus 1 standard deviation being 68%. And we talk about plus or minus 2 standard deviations being 95%. So far, we're just rounding to the nearest percentage. If I rounded that last one to the nearest percentage, what would I get? 100, but that's no fun because it doesn't leave anything in the tails for us to talk about. And so statisticians and finance professors alike fudge, and we call that last one 99%. And so now I'm going to, by the way, I'm a lousy artist, please forgive me. Okay, so I'm going to draw my normal distribution here. And we know that this is the mean. I'm going to call that 0. And then, what do we say was 68%?
Plus minus 1 standard
Yeah, plus 1, and I'm going to go ahead and use the population symbol, and minus 1 standard deviation. And then, between plus 2 standard deviations and minus 2 standard deviations is 95%. And then, minus 3 standard deviations up to plus 3 standard deviations is 99%. This is what you should have on your note sheet. And here's why. I'm going to be giving you some information on the exam that will allow you to either use this distribution or create this distribution, then use this distribution. And it's really not hard. I just showed you how to do it on your calculator, right? And if you don't have this on your note sheet, and you don't remember this, then you will think that I have left a piece of information out. So I've been teaching for a long time, and I taught a lot of China EMBA classes. And in one of those classes, we had a Mongolian lady. You might know her, I don't know. Her name is Amarashana. Anyway, back to the story. By the way, did you know that Mongolians usually only have one name? Yeah, isn't that cool? That'd be so much easier when your mom asks you to write your name on your underwear with one name, right? If you've ever been to camp, you know that story. Okay, back to the story. Okay, so here's what happens. During the exam, she raises her hand. And so I go up to her, and she's working one of these problems. And she said, she's not as nice as you are. She said, "You did not give me enough information to solve this problem." And I see this on her note sheet, and I go, "Yes, I did." "You did not give me enough information to solve this problem." And I said, "Yes, I did." And then she reaches for my lapels, and I dodge back. I was quicker then. I think she would have pulled me over the table. Now, why do I tell you that story? That story is to remind you that when you get to the exam and you get to the question, you're like, how am I supposed to figure out the probability of anything? Boom, normal distribution. Bam, it's on my note sheet. I'm good to go, right? Okay, now, the normal distribution, we said that we think stock return, we're going to assume stock returns are normally distributed. And we said there were only 2 exceptions to that. Number 1, we know it's truncated at minus 100%. And number 2, we said that there are slightly more observations in the tails than there should be. But for purposes of this class, you are perfectly okay thinking that stock returns are normally distributed. Now, here's what you need to know. Normal distribution isn't just about stock returns. So many things in this world are normally distributed. Anybody know what IQ is? What's IQ?
Intellectual quotient?
Yeah, or intelligence quotient is what we call it in the 70s. They probably changed the name since then, kind of like KFC. Now, back to the story. What is it a measure of? How blank you are.
Smart.
Smart. Does it measure your education level? No, man, it's your raw horsepower, right? That's the idea. Now, does anyone know what the average IQ is by design? 100. Most people know that. By the way, how did they come up with this number? French school children in the 19th century. They were the lab rats, right? This guy, Professor Smartacus, came up with this exam, and he gives it to these French kids, and he just assigns the value of 100 to be the average, right? So whatever score they came up with, he converted that to 100. And then he goes through and looks at all their stuff and does standard deviation. Now, this isn't a number he can control, right? Because he's got a random sample here, plus he's already assigned this 100 to be the middle, and lo and behold, he figures out the standard deviation of IQ is, do you know? Oh, close. 15. 15. So the standard deviation is 15. Now, knowing that, if I ask you what percentage of the population has got an IQ between 85 and 115?
68.
68%. You see how she did that? That's plus or minus 1 standard deviation. And what if I ask you what the percentage of people that have an IQ between 70 and 130? Yeah, it's 95%. And what if I ask you about the proportion of people that have an IQ between 55 and 145? 99%, right? In fact, these standard deviations is how we came up with some terminology in psychology. And what's bad is if you put a name on something and it has a negative connotation, apparently, eventually, this will become a bad word, right? Because there were words like idiot and moron. And at the time that they labeled them, these things didn't have a stigma associated with them. But of course, then people start using those words to describe people in a negative way. For example, minus 2 standard deviations was called mentally retarded. It was just a clinical term at the time. Are you allowed to go around and throw that on the street today? No, right? Now, the positive ones, it doesn't work the same way because people don't consider it an insult to be called a genius or whatever. But we can get up to, if we go up to like 130, I believe it's called gifted. And if you get up to plus 3 standard deviations, it's 145. What do you think it is? Starts with a G.
G.
Yeah, you're a genius, right? Does that make sense? And so this is how we've named these different levels. Okay, now I'm going to make this a little bit harder. I want to ask what percentage of the population has an IQ below 70? Now she's doing stuff in her head that the rest of you probably can't do in your head because she was probably taught math correctly. So here's what we're going to do. I'm going to give you a formula. The first thing we're going to do is figure out how many standard deviations away from the mean we are. And you could either call it T or Z. It's the same general idea. We're going to call it T here. And it's going to be equal to X minus X bar divided by S sub X. Now, X is the point on the distribution you're looking at. And I asked you what percentage of people were below 70. So in this case, 70 would be X. And then I'm going to subtract X bar. For IQ, what did we say X bar is? 100. And then I'm going to divide by the sample standard deviation. What did we say it was? 15. Okay, 70 minus 100 is negative 30. Negative 30 divided by 15 is how much? 2. And minus 2. By the way, the minus is important because it tells you whether you're over here or you're over here, right? And so when I ask you what percentage of the population has an IQ lower than 70, you're going to say, well, wait a minute, that is 2 standard deviations below, and I know that between plus and minus 2 standard deviations is 95%. That still doesn't tell me how many are over here without one more fact. Here's what you need to know about the normal distribution. It is symmetric about the mean. Symmetric about the mean. It's the same on both sides. It's the same on both sides. Symmetric about the mean. Now, what does that mean? It means that 50% of the observations are over here, and 50% of the observations are over here, and there are just as many observations in this tail right here as there are down here. So now that we know that, we can say, well, wait a minute. By the way, what percentage is under the entire curve? 100%, right? There are no observations in the world that are not under this curve. And so we're going to say, well, so this is 95% here. 100% minus 95% gives me what's in these two tails. Right here and right here. By the way, what's 100 minus 95? 5%. Now, knowing that if I add this tail and this tail together, that I get 5%, and knowing that those tails are identically the same size, can you tell me what percentage is in just one of those tails? Yeah, 2.5%. Now, if we had done this with the exact numbers, the answer would be 2.28%. I work diligently to try to make sure all your homework and exam questions are using the approximations, but occasionally an exact one flows in there. I guarantee you I will not make the choices such that you would have both, right? You'll be able to look at it and know what I'm doing. But I have tried really hard to make them all according to the approximations. Okay, so knowing that, what we can say is that there is 2.5% of people are in this tail. Therefore, there are 2.5% of the population that has an IQ lower than 70. What if I ask you what proportion of the population has an IQ of 70? Can I answer that question using the normal distribution? No. I cannot pick out any single point and say, what's the probability? Even 100? Right? We know 100 should be more likely than, say, 130, but I still can't tell you what proportion has exactly 100 because it's like a continuum, right? Okay, and that's, we like to say nobody is actually average, right? Nobody's going to hit this thing 100 dead on, unless purely by chance. Okay, back to the story. Let's ask a question here, and then we'll move off of IQ onto stock returns. I'm going to tell you that you are a genius. I have tested you all. You are geniuses. You have an IQ of 145. Are you happy? Oh, yeah. By the way, going up to people in bars and telling them you're a genius is not a good plan. Don't ask me how I know. Okay, back to the story. It's still good to feel that good about. You're fine doing that. So we've got 145 IQ. Now, the question is, what percentage of people on the planet are smarter than you? So let's see if we can figure this out. You have an IQ of 145. What is 145 minus 100? 45 and divide by 15. What's 45 divided by 15? Plus 3. Plus 3. So where are you at in this whole thing? You're over here. So let's actually use the exact for this. 99.74%. 99.74% are between plus and minus 3 standard deviations. What does that mean is outside of plus or minus 3 standard deviations? 0.26%, right? 0.26%, but that's 2 tails. How much is in each of those tails? Divide by 2, 0.13%. 0.13%. Okay, now, here's what I want you, by the way, are you feeling pretty smart at this point? Only 0.13% of the population of the world is smarter than you. You feeling pretty good? Yeah! Okay, now, I'm going to bring you down. Okay, are you ready? Get your calculator up, and we're going to say 0.13 divide by 100. We're going to turn that into a decimal, and just ignore the s sub x. So there's 0.00, wait a minute, that didn't work out right. 0.13 divide by 100. There we go. And now I'm going to multiply by 8 with 9 zeros after it. Why 8 with 9 zeros after it? Yeah, it's the population of the Earth, right? How many people on Earth are smarter than you? 10.4 million people. Do you feel quite as good about your situation now?
Yeah.
Not quite as good as you did just moments ago, right? Now, I have some good news for you. About half of those people are in areas of the earth where they don't have electricity or the internet. They probably didn't receive good education, so you will only have to compete with maybe 7 million of those people. It's powerful, this normal probability distribution. It works on all sorts of different things, and I don't want you to ever think the only thing you can do with it is stock returns. But let's talk about stock returns. In fact, what we've got up here on the screen is the normal distribution. It's for large stocks. And how do I know it's for large stocks? Well, the mean is 11.8%. And if you look back at our earlier slides, we said that the large company stocks had a mean return of 11.8% over that period starting in 1926. Okay. Let's see what else we've got here. Can anybody tell me what was the standard deviation of large stock returns just from looking at this slide? What's the standard deviation? Oh, very good. 20.5. Would you please share your magic trick with the class? How did you do that?
Like one standard deviation is 32.3 minus median and it's mean.
Mean, yeah. So here's what she said. She said, well, wait a minute. I know the plus 1 standard deviation is 32.3%. She says, and I noticed that the mean is 11.8%. So all I have to do to get the standard deviation is to take 32.3 and subtract 11.8. And she's absolutely right. Now, let's check her work. What if we take 11.8 minus 20.5? What do we get? We get negative 8.7%. That's the negative 1 standard deviation. So did I even have to tell you what the standard deviation was for you to be able to figure it out? No, you could do it from the numbers that are on the screen. Okay, now, here's how we talk about stock returns. What is the probability that your large company stock return next year will be between negative 8.7% and 32.3%? 68%, right? And what's your probability that your stock returns will be between minus 29.2 and positive 52.8? 95%. And what's the probability that your stock returns will be between negative 49.7% and positive 73.3%? 99.74%, or 99% if we're using the approximations. Now, that's all very easy. That's all very easy. But let me ask you this one. What's the probability that your stock will return, or that those stocks will return more than 11.8%? Yeah, it's got to be 50%, right? Remember we said this thing is symmetric, and therefore half the observations are above the mean, and half the observations are below the mean. Okay, now, what is the probability that the stock return will be less than 11.8%? 50%, right? It's the other side of that same coin. Now, so far, so good, so easy. But now it starts to get a little hairy. What is the probability that the stock will not lose more than 8.7%? What is the probability that the stock will not lose more than 8.7%? Now, the first thing you've got to do is translate English into math. When I say lose 8.7%, what's the return? Negative 8.7, right? That's the first trick there, is figuring out it's minus 8.7. Minus 8, so now we know where we are looking. Minus 8.7. I'm going to subtract the mean. What's the mean? 11.8. And then I'm going to divide by the sample standard deviation. How much? Oh, come on, we calculated it just a bit ago. 20.5, right? She gave us the answer. She told us 20.5. And how did we get that? 32.3 minus 11.8. Okay, if I take minus 8.7 and subtract 11.8, I get negative 20.5. If I'm doing my math wrong, let me know, please. Okay, yeah, this thing is going to be equal to not just 1, minus 1. Minus 1 standard deviation. And so that puts us right here. What's the probability that we will not lose more than? Which part am I talking about? Am I talking about this part
This
or this part?
big.
Yeah, this part, right? This is the part we're talking about. Will not lose more than. Oh, wait a minute. Not lose. Yeah, not lose more than. So if I'm over here, I'm not losing more than 8.7%. Are you looking?
You will not lose more.
So it's not lose more than. The probability, so where am I not going to lose more than 8.7%? If I'm over here, so what's the probability I will lose more than 8.7%? It's going to be this right here. What's the probability I will not lose? Whoop, right? English is what makes this so hard. It's not the math, it's the English. Okay, so what's the probability I will not lose more than 8.7%? It's starting here and going this way. Now, there is two ways we can go about this. Number one, we can figure out how much is in this tail and subtract it from 100%. Let's do that way let's do that the first time. So we've got between plus and minus 1, we've got 68% of the observations. What does that mean is left in those tails? What's 100 minus 68?
Yeah, 32.
32, right? Now, we know that 32 represents both of these tails. What's 32 divided by 2? 16, very good. And so we know that we've got 16% hanging out over here. And we know that this overall thing is how much? 100%. And so all I do then is take 100 minus the 16%, tells me that there's an 84% chance that I will not lose more than 8.7%. Oh my goodness. So, lose minus not is the other thing, right? So those are the things you've got to do to make that work. Let's see. Oh, I was going to tell you the other way. Remember, this thing's symmetric. So we know that half is up here. How much is from here to here? 50. And then we also know that between here and here is 68%. What do you think is between here and here? 34%, right? Because 68 divided by 2 is 34. What's 50 plus 34? 84%. There are almost always two ways to do every single one of these problems. Which way should you use? The one that works best for you. Once again, I don't care how you get your answer as long as you don't cheat. As long as you can get the correct answer using whatever your messed up methodology is, God bless you, go for it, right? Yes?
Can you do the second part again?
The second part again?
Yeah.
Okay. Remember we said this thing's symmetric. It's the same on both sides. And we're trying to figure out what is from here over. So what I'm going to figure out is what's from here over, and then I'm going to figure out what's from here to here. How much is from here over? Yeah, 50%. Now, we said that between plus and minus 1 is 68%. And we said that it's symmetric, meaning that half of that's going to be over here, and half of it's going to be here. And so we're going to take that 68 and divide by 2. And when we do, what do we get? 34. Yeah! And then when we add this 34% with this 50%, what do we get? 84. 84. Same answer either way. Other questions? What is the probability that the stock will not return more than 32.3%? What's the probability that the stock will not return more than 32.3%? So 32.3 minus 11.8 is 20.5 divided by 20.5, which is plus 1. And so we're right here. What's the probability it will not return more than?
Is it including minus or?
Oh yeah, not return more than. So would this be a lower return? Yeah, right. What's the probability it will?
Saying 84.
Yeah, so if this is going to be 84%, the probability that it will not return more than is going to be this piece over here. Now, you guys, I'm making this look easy for some. And those people are like, I get that. I guarantee you, you don't. You're going to need to watch this. You're going to need to watch the examples that I have in my example videos. And then you're still going to have some questions, and that's when you're going to reach out to me. And I'll point out words like lose and not and things like that. I'll be nice about it. My point to you is this. This is not easy. This is not easy. This requires a lot of mental gymnastics. By the way, I've been doing this now since 2003. Do you think I was able to present this material flawlessly from the beginning? Oh man, no, I screwed up all the time. You almost got me screwed up earlier today, right? He's a smart, I mean, look, he's got a beard, right? He should be right. But no, right? So what does this mean for you as someone who's relatively new to this sort of thing? You need to practice. Right? You need to practice. By the way, what should you have on your note sheet? I hope you're a better artist than I am, but that's what you should have on your note sheet. Questions? Now we're moving on to the arithmetic average versus the geometric average. Arithmetic is just where we add the numbers up and divide by the number in the sample. It's what we've already been doing. And for all of these statistical calculations, when we subtract out x bar, it is always the arithmetic mean or the arithmetic average. It's the one your grandma can do. Now, it has some issues, and I'm going to point those out to you, but I'm going to introduce a new measure here that has different issues but gives you different information. And that's called the geometric average. The geometric average. Now, by the way, with arithmetic average, does it matter whether I use decimals or percentages? No, as long as they're all decimals or they're all percentages, it's all good. But what about geometric? Notice that in the formula for geometric, we are taking those returns and adding 1. It very much now matters whether we use decimals or percentages. If you use percentages, it's not going to work. It's not going to work. And so the returns, that's the first note I want you to make, is that the returns in the geometric average formula are all in decimals. The returns in the geometric formula are all in decimals. Okay, now here's how we're going to get our geometric average. We're going to take each one of those returns in decimal and we're going to add 1 to it. So if the return was 15%, I'm going to have 1.15. If the return was negative 15%, I'm going to have 0.85. 1 minus 0.15. It gives me 0.85. And so these things are going to be on either side of 1. So if you come out with something less than 1, it means the return must have been negative. So that's the first step. We do that for every single one of those returns. And then what we do is we take each one of those 1 plus r terms and we multiply them all together. We take each one of those 1 plus r terms and we multiply them all together. Ms. McComas, are you okay?
Yeah.
Okay, she got that glazed look. Yeah. I used to be able to bring a glass of water and throw it at students, but then they said, I can't do that anymore because apparently some people are allergic to water. Who knew, right? Okay. I just said that to wake you up, right?
Yeah.
Okay,
I
very
worked,
good.
I worked early this morning.
You worked early this morning.
Yeah.
Where were you working?
I work at the hospital, but it's like 4 a.m. shifts
Oh!
every day. I know. So it's pretty brutal.
Oh!
Yeah.
Folks, this is the value of education.
Yeah.
Once I got a bachelor's degree, the only time that I ever spent, if I got called out in the middle of the night for like the oil job is going down and down. That only happened like 3 times, right? But if you don't, there you go,
Yeah.
4 a.m. for the rest of your life.
I know, it's pretty bad. And I don't get enough sleep either. So.
Yeah, see, that's the other problem,
Yeah, I go to
right?
bed too late.
So I'm going to tell you the value of the midday nap.
Yes. That's after this class. It's like an awkward time though, because I can't sleep before this class, but it's after. So I come and I'm like, oh.
So I had a colleague that was teaching at 8 a.m. And I'm like, and I asked the students that were in there, I'm like, how do you guys do this? They're like, yeah, we just stay up for this class. Okay. Back to the story. Where the hell were we? Oh, okay. We're multiplying all those 1 plus r terms together. And then what we're going to do is take it to the 1 over n power. By the way, n's the sample size, right? And so if we're looking at a sample size of 4, like we were earlier, this is going to be to the 1/4 power. To the 1/4 power. And then we're going to subtract 1. Why do we subtract 1? Remember we added 1 to all of those r terms to begin with?
Yeah.
Now we're getting rid of it. We're going to subtract it. Now that we've taken this to the 1 over n power, we subtract it, and now we get a decimal average return, but it's the geometric average. And so I will walk through a calculation of this with you. So here is our example. We have time 0, 1, and 2. And we have prices at each one of those times. The value of the portfolio is 100 at time 0. It's 50 at time 1. And it's 75 at time 2. So now what I want to do is figure out, well, what is the return for each one of those situations? Now, I cannot find a return at time 0, and here's why. In order to have a return at time 0, I have to know the price at time -1. Do I know the price at time -1? No. Why then have they given me this information? I've got to have this information in order to be able to figure out the return at time 1. By the way, what's the return at time 1? It's going to be the price at time 1 minus the price at time 0, so that's -50, divide by the price at time 0. Remember that we said, yeah, the return at of period t is equal to the price of t plus 1 minus the price at times t divided by the price at time t. Okay, so that's for period t, that's the return. Okay, so to get this, we're going to take 50 minus 100 divided by 100. Actually, this should be what, t plus 1? Yeah. Okay, so this gives us, if I've got minus 50 divided by 100, what's my return? In a decimal. Minus 0.05. 0.5. Right? 50 divided by 100 is 1/2. So we've basically lost half. Whew. Well, that sucks. Let's see what happens in the next period. At the end of the period, we've got 75 minus 50 gives me how much? 25. And then 25 divided by 50 is how much? 0.5. Okay, so now I've got these two returns, and if I were to figure out what is the arithmetic average, what would I get? Yeah, add them together, divide by the number of observations. If I add these together, I get 0. At this point, does it matter how many observations? No. No matter what I divide by, I'm going to get 0. So the average here is 0. Woohoo! You thought you were in trouble, but you actually had an average return of 0. Do you feel actually good about that, though? Does it look like a return of 0? Here's the problem. Arithmetic average does not take compounding into account. Arithmetic average does not take compounding into account. And that's why we can lose 50% and gain 50% and not be back at the same place. Example. This is after the financial crisis. I'm watching CNBC, and I can tell that the person who's talking got their job because A, they have a journalism degree, and B, they're good looking. It wasn't because they had any idea what they were talking about. And here's why. This lady says, well, at the peak, or at the trough, after the financial crisis, the S&P 500 was down 30%. But we've gained 30% since then, so we're right back where we started. Is she right? No. Here, think about this. Let's say the S&P 500 was 100 when the whole thing started. If it was down 30% at the trough, 100 minus 30% is 70. Now, what is 30% of 70? 21. So if this thing is up 30%, it's 70 plus 21. We're only up to 91. We are still down 9%. This woman had no idea what she was talking about. And once again, good looking, journalism degree. A lot of people, this doesn't work for them mentally. But we have to keep these things in mind. Okay, now let's talk about how we can figure out what is the geometric average. That's the one that tells us the effect of compounding. And we're going to add 1 to each one of those returns. So get your calculator out. What is, let's say 1 minus 0.5. That's the first one, right? And so it's just 0.5. And I'm going to multiply by open parentheses 1 plus 0.5 close parentheses equals. So I've got 0.5 times 1.5. And that gives me 0.75. Now, if I'd had a bunch of those, I would just keep doing that. I could do that for as many returns as I want. But in order to find out the geometric average, I'm going to have to take it to the 1 over n power. How many returns did we have here? 2. What is n? 2. So we are taking this to the 1/2 power. Now, some of you who are math geniuses may recognize that to the 1/2 power is the same as square root. Yeah, don't feel so smart though, because eventually we're going to get to where we have 7 observations, and what are you going to do then? All right? So let's walk through this as if we had more than just 2 observations. Here's how I'm going to do it. The first button I'm going to hit is y to the x. Do you see it? It's right over the number 9. And then I'm going to hit the open parenthesis key. I'm going to say 1 divide by n. N in this case is 2. I'm going to close the parentheses, and then I'm going to say equal. 0.866. Now, most of the times, one of the answer choices on the exam would be something like 8.66%. Why? Because students often forget that we have more steps to go. What's the next step?
Subtract.
Yeah, we got to subtract 1. And that brings me to 0.1340%, basically negative, not percentage. In order to get percentage, I have to divide by 100. And there I go. Oh crap, now I need to multiply by 100, right? That's where we should be. Minus 13.4%. Okay, now does that make more sense? We started at 100 and after 2 years we're at 75. It makes a boatload more sense. First of all, we know that return is negative. And secondly, if I just had to no-brain this thing, I would say, well, that's an average drop of 12.5% per year, right? To get from 100 down to 75 is 25% drop. Just assign roughly half of that to each year, and I'm looking at about 12.5%. So it makes perfect sense when I see negative 13.4%. And there's another way we can get after this. Take a look. We can hit second, clear TVM. I have my value at the end of 75. 75 future value. And I have my value at the beginning of 100. Remember the sign convention, got to make it negative. Present value. How many years? 2. And then what do I compute? Compute I per y. Now we're at negative 13.4%. Does that number look familiar? Yeah, this is the number your calculator gives you, right? Now, you say, whoo, this is going to be easy. I never have to do all that 1 plus r crap. Wrong. Wrong. You're going to see in the example, or in the homework or the practice, I think it's the homework, that I throw one of these out to you that also has dividends in it. It also has dividends in it. And it's not the easiest thing in the world, but fortunately, I have recorded an example video. So if you'll look in the examples folder, you'll be able to see that there and walk through it. Here's the other hint that I'm going to give you about that. The way that they show dividends in that problem is not normal. They do it like this. Notice in class, whenever I write a decimal, what do I always write to the left of it? 0, right? I want you to be able to spot that. If I don't put it, you may miss that decimal. And so a lot of students end up thinking, instead of thinking this is 0.25, they think it is $25. By the way, if you look at the price, and the price is much smaller than the dividend it's paying out, there's something wrong, right? But even that, just take a look really close, you'll see the little decimal, and you'll be so much better for having done that. Okay, question so far?
So when you're taking it to the 1 over whatever power, if you had, say, 7 observations, that'd be like taking it to the 6th root?
No, it'd be taking it to the 1 over 7. So it would be the 7th root. Yeah.
But it's 1 over n minus 1.
Nope. You're thinking about sample standard or sample variance.
Yeah.
Oh yeah, don't get these things screwed up in your head, man. Yeah. Notice that it's in the formula, it says to the 1 over n power. And then the minus 1 is over here by itself. Yes?
Once you take your decimal that you converted from a percentage, and you add 1 to that percentage.
Right.
For each of your observations. You do that, and then you sum the product of each of those.
No, you multiply those things together.
Right, once you multiply them, but I'm saying you take the sum of those products, of those observations.
No.
No.
The word sum means add.
Right.
So what you're
And that's
doing,
what I'm saying.
you're taking the product of sums, not the sum of products. That's what you need to do. You need to, so if I'm going to multiply these things together, the thing that I get out of it's going to be called the product.
Right. But then
Each one of those individual sums, we're going to multiply to get this product. And now we're just getting into English. Okay, here's what I'm going to do.
No, I mean, I understand the meaning of sum and product.
Oh, okay.
This is, what I'm trying to say is that based on this example in this book and what we're talking about here, because you get the product, right, from these.
We're multiplying all those things
multiplying that
together.
decimal by its one, its itself plus 1.
Okay.
Okay, that's the product.
You're going to multiply all those things together, and that gives you the product.
For that one observation.
No, that's a sum. A product is what comes out of multiplication. A sum is what comes out of addition. Okay.
I'll talk to you about it.
No, that's okay. Here, in fact, I was getting ready to tell you this. Here's the best way to do this. For each of those returns. I'm going to, let's say it's negative 15%. I'm going to take minus 15 divided by 100. Now my calculator is going to say minus 0.15. And then I'm going to add 1. Okay, so that's the sum of those things. Add 1, right? Okay, I'm going to store 1. And then the next one, let's say it's plus 10%. And so I'm going to take 10 divided by 100, which is 0.1 out. I'm going to add 1. So that's 1.1. And I'm going to say store 2. And the next one, let's say it's minus 25%. I'm going to divide by 100, so minus 0.25. Add 1 gives me 0.75. And I'm going to store 3. What's my next step?
It's the same thing, you multiply, then you get your product, and then you store 4.
So we
Then you
recall,
can go back and sum those by saying recall 1 plus recall 2.
we're not summing them.
You're not.
Recall 1 times.
Oh, it's gonna be-
Recall 2 times.
So, okay.
Recall 3.
That's what-
And once we do that, because we've got a sample size of 3, now I'm going to take it to the 1 what power? 1
2.
Yeah,
1/3 power, right? I'm going to take it to the 1/3 power. So how do I do that? I'm going to hit the Y to the X button. I'm going to hit open parentheses. And I'm going to say 1 divide by 3, close parentheses, equals. Boom. And now, what's the thing we need to do next? Subtract 1. Are we at our percentage return yet?
No.
One more step. What do we need to do?
Multiply by half.
Multiply by 100%. And that puts you where you need to be. Okay. So that's how we're going to do this. Now the question is, why one versus the other? And it turns out they answer different questions. The arithmetic average answers this question. What is your return in an average year over a particular period? So, in an average year, let's see, I've got 1 year that's down 50%, 1 year that's up 50%. In an average year, my return is 0%. It makes perfect sense as an answer to that question. Now, what about geometric? It answers the question, what is your average compound return per year over a particular period? In this case, the period is 0 to 2. What is our compound average return? That's where we get into this situation using the compound return, or the geometric average. Now, let me tell you a couple of things here. Number one is that the compound return, assuming an average, positive average returns, a compound return, geometric compound, the geometric average will always be equal to or lower than the arithmetic mean. The compound average, the geometric average, will always be equal to or lower than the arithmetic average. In fact, the only way they're going to be equal is if there is no change whatsoever in the return. If the return is 8% per year for 4 years, we've got 1.08 times 1.08 times 1.08 times 1.08 to the 1/4 power. Subtract 1, you're going to find that that's 8%. And if we do that also, arithmetically, 8 plus 8 plus 8 plus 8 is 32. What's 32 divided by 4? 8. And so you're going to see that if there's no variance whatsoever, if they don't change at all, that those will be identical. Otherwise, what we see is the geometric average falls lower. So let's take a look here. I'm going to do an example. And I'm going to make some of the returns 0 and some of the returns 8. So we're going to have 2 0 returns and 2 8 returns. 0 plus 0 plus 8 plus 8 is 16. What is 16 divided by 4? 4. So our arithmetic average return is 4%. If what I'm telling you is true, the geometric average return should come out something less than 4. So here we go. 1 times 1.08 times 1 times 1.08 equal. Okay, now I'm going to take it to the what? 1/4 power. 1 divided by 4. Oh, please turn your phone off. I'm getting 1.039. What's my next step? Minus 1. And then what do I need to do? Multiply by 100. Remember, we said our arithmetic mean was 4. And now we're looking at something less than 4. The geometric mean will always be less than the arithmetic mean if there's any variation at all. And of course, we're assuming average positive returns here. Now, what does that mean? We can say, well, it's possible that your arithmetic average is probably too high. When we were talking about what's really going on over here, we said that 0 was probably too high as a good representative return for this set of returns. And it's a possibility that the geometric might give you the illusion the other way, that it's possibly too low. Now, that also has to do with how long. So we talk about that the arithmetic is probably too high for longer periods, but the geometric is possibly too low for shorter periods. The explanation for that longer, shorter thing is very complex. Fortunately for you, I have dropped an academic paper in the folder for Chapter 10, and you can go read that if you want to know all the nitty-gritty. But here's what I would advise you to do instead. On your note sheet, write arithmetic, the answer, the question that it answers, and then write that last line, probably too high for longer periods. And on your note sheet for geometric average, you say, there you write down the question and then below for shorter periods. Or you can go read the boring academic paper to get all the nitty gritty. Up to you, totally up to you. I'm pretty sure I know which way most of you are going to go. Questions? Question?
It may be answered in the paper, but what's geometric about it?
Oh, why is it called geometric? That's a good question. If it wasn't already 12:15, I'd just Google it and tell you all. If you are interested, Google that, and maybe next time you can share it. Cool. Other questions? Thank you. Oh!
You're gonna have to know half standard deviations for this class.
No, good question. I will not throw anything at you that is like 2.5 standard deviations above the mean. And the reason is, if I did that, you would have to have a table to be able to answer the question. And I'm not going to give you a table. So there you go. What have you got instead of a table? Right there.